Welcome everybody to the Arc Science seminar. Today's speaker is Sridhar P Narayanan from the Institute of Mathematical Sciences, Chennai. He's going to talk about an interpretation of multiplicities of the trivial and sign representation in while modules of hook shape. Sridhar, please.
Thank you. Good afternoon, everyone, and thank you for this opportunity to present this work. Today, I want to talk about the multiplicity of the sign representation and the trivial representation in irreducibles of GLN indexed by hook shapes when restricted to the symmetric group Sn. This is work that was done in conjunction with Shraddha Srivastava, Digjoy Paul, and Amritanshu Prasad. And a detail of some of the proofs that I've omitted here can be found in our paper, Character Polynomials and the Restriction Problem. Just some notation before we start. An Sn irreducible, that is an irreducible of the symmetric group Sn, is denoted by V lambda, where lambda is a partition of n. An irreducible of GLN is denoted by W mu, where mu is a partition with at most n parts. We use the Rubinius notation to denote hook shapes. So the Rubinius notation K vertical dash L denotes the hook partition K plus 1, comma 1 raised to L. Okay. So there were three steps, roughly speaking, to how we did this. First, we obtained the relevant character polynomials, and then we obtained generating functions for the moments of those character polynomials. And finally, we interpreted the generating functions to find an involution. So let's begin with the first of those steps. Let's begin with character polynomial. So in order to define character polynomials, we must first define some elementary class functions on permutations. So we define these class functions xi on a permutation. Xi on a permutation is simply the number of I cycles in that permutation. So for example, xi of the trivial or xi of the identity permutation of Sn would simply be n. X1 of the identity permutation of Sn would simply be n, because x1 would count the number of one cycles or fixed points, right? So once we have defined these functions xi, it makes sense to talk about polynomials in these functions. And it makes sense also to talk about the evaluation of these polynomials on permutations, because each of the xi's can be evaluated on a permutation, and so the polynomials themselves can also be evaluated on permutations. Now, consider a sequence Vn, which is indexed by, let's say, positive integer. So consider a sequence Vn, where each Vn is a representation of Sn. So V1 is a representation of S1, V2 is a representation of S2, etc. Such a sequence is said to have eventually polynomial character if there is a polynomial in the variables xi, or rather the functions xi. So if there is a polynomial in the functions xi, such that that polynomial evaluated on a permutation gives the value of the character of the relevant Vn on the permutation. So rigorously speaking, eventually means for all positive integers n greater than some fixed positive integer capital N, we have this condition. The polynomial, there exists a polynomial which is called the character polynomial, and that polynomial evaluated on a permutation of Sn, on any permutation of Sn, is equal to the character of Vn evaluated on the same permutation. Okay. So that is a character polynomial. Let's look at an example to familiarize ourselves with this notion. Let's look at the example of sim2 of Cn. Now, sim2 of Cn, you can think of elements of sim2 Cn as two-element multisets, where the two elements come from 1 to n, right? So Sn has an action on such elements. It just acts by changing the labels of these elements. And so if we are interested in the character of sim2 Cn evaluated on a particular permutation, we just need to evaluate which multisets this permutation fixes under this action, right? So let's look at a motivating example. Consider the permutation which has 1, 2, 3 as fixed points, and it has 2 cycles, 4, 5, and another 2 cycle, 6, 7. So this permutation would fix 3 types of multisets. In the first type of multiset, we choose a fixed point of the permutation and repeat the element twice in the multiset. Then the action of W on this multiset would simply fix it because it fixes 1 and both the elements are 1. The second type of multiset that it fixes is by choosing 2 distinct fixed points. For example, you see here we've chosen 1 and 2. When W acts on the multiset 1 and 2, it fixes both 1 and 2. And the third type of multiset that is fixed by such a permutation would be the elements in a 2 cycle. So we pick a particular 2 cycle and both of its elements are members then of the multiset. So let's pick this 2 cycle 4, 5. Then the multiset obtained by this is 4, 5. And if W acts on this, it takes 4 to 5 and it takes 5 to 4, but it fixes the multiset, right? So given this example, given the permutation in this example, these are the 3 types of multisets that it fixes. So let's think of a generalized permutation which has x1 1 cycles, x2 2 cycles, etc. How many permutations does that fix? Well, first there's the first type of multiset. So the first type of multiset is obtained by choosing 1 cycle, right? So out of x1 1 cycles, you must pick 1 and then repeat the element twice. Or we could pick 2 1 cycles and both of those elements will be members of the multiset, and such a multiset would also be fixed. And this corresponds to, well, x1 choose 2, we're picking 2 fixed points. The third type of multiset is obtained by picking a 2 cycle, and then the elements of the multiset are simply the elements of the cycle. And so we must pick a single 2 cycle. So these are the 3 well, this is the character polynomial of sim2cn. So what we've done is we've considered a generalized permutation, a general permutation with x on 1 cycles, x2 2 cycles, etc., and found the number of multisets that is fixed by it, right? So this polynomial, which we call the character polynomial of sim2cn, we denote by h2. And in general, we will denote the character polynomial of sim_kcn by hk. I hope this example is clear.
So I have a question in the last slide.
Okay.
Yeah. How do we get that x2?
Right. So this is the third type of multiset. So we simply pick a 2 cycle and then the element of this 2 cycle become the element of the multiset. So when this permutation acts on this multiset, it will take 4 to 5 and it will take 5 to 4. So the multiset will remain unchanged because it's still 4, 5.
And if we have a 3 cycle in place of that, what will happen?
Well, a 3 cycle wouldn't be fixed. So suppose we have
instead we change the W and we have a 3 cycle.
So let's add a 3 cycle here.
Yeah.
So we can add 8, 9, 10. But we could not form a multiset which would be fixed in this way. If we chose any 2 elements out of 8, 9, and 10, when W acts on this, it will take this to 9 and 10. So it wouldn't be fixed. So we need a 2 cycle so that the 2 elements can permute among themselves. A 3 cycle would come into play if we had something like sim3cn. Then it would be fixed.
And this polynomial itself is claimed to be the characteristic polynomial of
the character polynomial. Yes, because if you evaluate it for all n, for all n eventually, so the past some initial value, I think probably 2. I think 2 is probably the initial value here. So for all n is greater than or equal to 2, if you evaluate this polynomial on any permutation, you get the character of sim2cn on that permutation.
Okay.
I think this one works for all n. It's actually polynomial on the
no, but then you don't have x. If you had n equals 1, you wouldn't have these 2 cycles.
Yeah, but then x1 choose 2 would be 0.
Oh yeah. Right. So I think this probably works for all.
Thanks. Thanks.
Okay. So we won't find in this talk, we won't try to find the character polynomials for HK and EL. If you like to see details on this, there's a paper included in the bibliography. We just state it here. So HK is given by this expression, the sum of these double brackets, we call them X multi-choose beta. I'll just unpack what all of this means. So it's the sum of X multi-choose beta over all partitions beta of K. And similarly, the character polynomial for wedge L, we call it EL, is the sum over all partitions of L, negative 1 raised to the size of the partition minus the length of the partition into X choose lambda. Now we've written it in this way, is it's sort of a shorthand notation. So let's kind of unpack this. So given if beta is written in the exponential notation as 1 raised to b1, 2 raised to b2, etc., then X multi-choose beta, or rather let's start with the easier one. So X for X choose gamma, if gamma can be written as 1 raised to c1, 2 raised to c2, etc., that means it has C1 parts of length 1, C2 parts of length 2, etc. Then X choose gamma is just shorthand for Xi choose Ci, the product of Xi choose Ci. So this is X1 choose C1 into X2 choose C2, etc. That's what we mean by X choose gamma. And we mean a similar thing when we say X multi choose beta. We mean just this product in each of the, say, coordinates. And what we mean by multi-choice is simply it's the number of ways of picking a multi-set of some size. So it's this multi-choice coefficient. Right. So if if A choose B is the number of ways of choosing a set of cardinality B from A elements, then X multi-choose, or sorry, A multi-choose B is the number of ways of choosing a multi-set with B elements from a set which contains A elements. Right? So these are the two generating functions, and we can use an identity that's probably well known on the symmetric function side. So to obtain the character polynomial for wedge KL, right? So corresponding to a hook shape KL, we have this irreducible, this GLN irreducible, which we restrict to Sn, and that is in that sequence is an eventually polynomial one. It has a character polynomial which we denote by SKL, and we use this identity, which is probably known on the symmetric function side. This just amounts to SKL equals -1. It's the exact same thing. H J goes from 0 to B. So we use this identity, which is also true for character polynomial. So we can, using the character polynomial for HK and EL, we can get an alternating sum, which is the character polynomial for WKL. So the irreducible corresponding to the hook shape, right? So this is a virtual sum because it has a sign associated to it, right?
One second. Could you go back one slide? What is that B there in the sum?
In the sum,
J equal to 0 to B.
oh, I'm sorry. Sometimes we use B for this. I mean L. Sorry, I mean L in both places. Right. So this is the first step. The first step is obtaining character polynomials. If there are no doubts with this first part, we can move on to the next step.
Just hold the. Could you go back?
Sorry.
A little. So the L determines the number of terms in the sum. But the
Yeah.
K, huh? So L
Well,
and K
there will
have
be,
different roles together, sort of. L
yes,
determines the number of terms, right? Or L plus 1 is the number of terms.
right. It will be L plus 1 because it
L
starts at
plus
0.
1 terms, and but that the K plus 1. Okay. Mhm. Okay, which is K? Okay, K is this,
Uh,
and okay, K is the arm, and L is the leg. Okay,
right.
got it. Thank you.
Okay. So once we've obtained the character polynomials, what we want to do is find the moment of character polynomials. So if you have two character polynomials, P and Q, then the moment is just given by this expression here. And this expression is just the inner product of two symmetric group characters, right? Well, first of all, they're real valued, so the conjugate sign goes off, and then the cycle type of the inverse of a permutation is equal to the cycle type of the permutation. So that's how we get this expression. So this moment is just the inner product of symmetric group characters. And when we take this moment, especially with an irreducible representation, we will get the multiplicity of that irreducible representation. So if Q were taken to be the character polynomial of an irreducible representation of the symmetric group, and we took the moment at n, then we would just get the multiplicity of that irreducible character in Pn or Vn, right? So we use this fact to form the moment, to define the moment and the sign moment. So the moment is just the inner product of P with the trivial representation. So it's just the trivial representation is 1 on everything. So it's just this expression here. So the moment gives the multiplicity of the trivial representation in Vn. That is, the moment evaluated at n gives the multiplicity of the trivial representation in Vn. Right? Similarly, the sign moment is simply the inner product with the sign character. Right? So we have the sign character contributing this first term. So the sign moment is just the multiplicity of the sign representation in Vn. Right? So that is the moment evaluated at n. Is that? So this is the concept to taking in the range where the polynomiality exists. So these are eventually polynomial characters. So for any n larger than the initial n, we do this. Okay. So given these moments, we are interested in computing generating functions for these moments. Uh, the bulk of this talk won't concentrate on the generating functions themselves, on deriving these. We just state them here. Uh, and we will state them later on as well. But this is the layout. We saw earlier that SKL can be written as an alternating sum of HKEL type term, right? So it was H of something times E of something else. And so we find an expression for the moment and the sign moment of these HKEL terms, which is here. It's this generating function. You can see they're both closely related. The differences between them is in the trivial moment, or in the moment, the u term is in the numerator, and in the sign moment, the u term is in the denominator. And that's, I think, yeah, that's pretty much the only difference between them. This rectangular bracket around vk ulzn indicates the coefficient of. So the sign moment is the coefficient of vk ulzn in this generating function. And similarly, the moment is the coefficient of v raised to k, u raised to l, z raised to n in this generating function, the first one. And using these, we can we can find the moments for the irreducible GLN modules for these SKL. We can find those just using the fact that the moments distribute across sums, right? So it's just the alternating sum of the individual moments. Right? So this is basically the setup. So what we're going to try to do now is associate each such term to a combinatorial set, and then define an involution that cancels out most of the terms. That's basically the trick. Okay. So before I move on to the third step, are there any questions just with the generating functions?
So there's a question from Aritra Bhattacharya. He asks whether it's for large n or for any n.
Right. Right. So this is for all n that's in the range of the polynomiality. So we said that these are eventually polynomial characters. So after some initial capital N, then the polynomial predicts the character value. So
No,
this would be for all.
But actually, I think it's true for all n.
In this case, because as you
For
said,
these formulas are for all n. There's no.
right, because as you said, it's not
Yeah.
just eventually polynomial, it just is polynomial.
Yeah.
Right. But in general, if it was an eventually polynomial character, this moment, taking the moment of the character polynomial would only make sense where the n is great, is the n is in the range where the character polynomial predicts the character.
No more questions on the chat. So.
Okay. Sorry. So we've obtained these generating functions, and the last step, the step that we'll be expanding on in this talk, is just how to interpret them and then an involution on them. So what we do with the character, so we're going to see how to visually represent this generating function, right? So what we do is all of the terms are marked on an axis.
Just to slow you down, Sridhar, this question
Okay.
is mainly to slow you down, not too much. So, for example, I could ask for how many copies of the standard are there, right?
Yes.
And do you have an answer in that case as well?
I don't have an answer ready, but the standard, I think, is the trivial plus, I forgot what it's said. But if you can express a standard into irreducible components, then we can
No,
just...
I mean, by standard, I don't mean the defining. I meant the irreducible in the defining.
I'm sorry, I don't... what does that mean? The irreducible in...
For Sn, it is n minus, the partition is n minus 1, comma 1.
Right.
So
okay, so you want the multiplicity of that representation in SKL?
In your eventually polynomial representation. That would make sense, right? So you would just try to do the moment of that instead of taking the inner product with the trivial or the sign, you would take inner product with that thing, right?
Right.
And like I said, it's just to slow you down. So you have theorems also relating to those, or it is mainly trivial and sign?
Well, in my thesis, we have generating functions for just the multiplicity of any irreducible Sn. So we have multivariate generating functions for any of them, but those are pretty complex, so we can't get any interpretations out of them. Like,
Okay.
But we have generating functions, and I can mention those at the end.
Okay. Like I said, it was just to slow you down a little bit.
Okay, thanks.
Yeah.
Okay, so we're going to look at how to visually represent, say, a monomial that comes out of this generating function. What we do is we mark each term in the product. We mark it based on the value or based on the exponent of v. So the v raised to j terms are marked on the jth level on this vertical axis, and the ones that come from the numerator are marked in red, and the ones that come from the denominator are marked in blue. So before we remark on the coefficient, let's do an example. So here we are considering a term that comes from a product of this kind. So the first two are from the numerator. So we've chosen a v raised to 0 z and v1 z from the numerator. And the other three terms are from the denominator. And we want to mark them on this, I guess, the axis. So what we would do is we would look at all of the terms that come from the numerator and we will mark those in red. So here we would look at v raised to 0. So at the 0th level, we'll put a red line. It's not a line. Right. So we put a line on the 0th level and there's a v raised to 1. So we put a line on the first level in red, which indicates that these come from the numerator. And the terms that come from the numerator are distinct, right? I hope that we can see that because none of these are repeated. So we can only choose a level once from the numerator, whereas from the denominator, you can choose it multiple times. Right? So we've marked the numerator terms, and then the denominator terms are the ones we mark them in blue. So there's a v raised to 1. So we mark a blue line on v1. There's another v raised to 1. So we mark a second line on the first level. And then the last one is v raised to 2. So we mark it on the 2, right? So this is how we go from a particular term to a representation of that term on this axis, right? And then we can read off pretty much all of the information from this figure that we obtained here, as we can do here. For example, we can read off the terms here. So this would involve a term. There are 3 terms from the denominator because there are 3 blue lines, and there are 2 terms from the numerator because there are 2 red lines. So what are the terms from the denominator? There are 2 on the 0, which would correspond to u v raised to 0 z.
For a minute, could you go back to the previous slide, please? I don't understand how you can get, see that j is bigger than or equal to 0. There is one term, one factor for every.
But if you expand this, it will be 1 plus uvjz plus uvjz square plus uvjz cube, etc. So we can take any number of terms from each of the 1 upon distinct term. It will contribute any number of terms.
No, I'm a little lost. Vj. V1. Okay, j is bigger than or equal to 0. Okay. But you will get v, so you're checking for v0 twice. Okay, got it. Okay. Okay, thanks.
So we have a u v raised to 0 z, and we take that twice because there's 2 lines on 0. And then the final one is a u v square z. Every term contributes a z. The z is just there to keep track of the total number of terms, and the u is there to keep track of the total number of blue terms.
Sridhar, how do you get u v1 z twice?
In the first example?
Yeah.
No, I started with this. So this was just, if I have a product of this kind, I can represent it on the axis.
Okay. I guess, okay.
And then this is doing the reverse thing. This is starting with a figure and then trying to find the terms.
Okay, but the first kind you cannot actually get, right? Because u v1z is only once.
No,
right?
we can get this. We can get this.
Can you
it's from the because it's from the denominator. The u terms for the sign moment, the u terms come from the denominator. So if I
there's only u v1z.
So if I had 1 upon
v square.
Yeah, 1 u v1 z then this will expand in the numerator as 1 plus u v z. I'll just u v z square
Yeah.
plus etc. So this corresponds to basically taking the u v z square here.
Oh, that's a product, huh? Okay.
Right. So from each term in the product, I must choose one term, and the denominator terms in the product, they expand as a sum of a geometric series. So I can take
Okay,
any
okay.
power.
No, thanks, because okay, okay. I didn't realize that those could come from different.
Oh no, these come from the same one. Maybe.
Same. Okay, okay. I mean, you could take. Okay, okay. Thanks. Go on.
So, right. So here we have two v zeros and one v square. That's from the denominator. From the numerator, which just you write it in red, we don't have a u because the u only accompanies terms that come from the denominator for the sign representation, right? So what we'll have is a v raised to 0 z and a v raised to 1 z, right? Because there's a line on 1 and there's a line on 0. The red lines will all occur on different levels. They can't occur on the same level, but the blue lines can occur on the same level, and any number of blue lines can occur on any level. And then we can read off all of the information from just this figure. For example, if you want to find k, that would be the total size of this partition, right? So it will be 2 plus 1 plus 0 plus 0 plus 0. So it will be 3, right? So 2 plus 1 plus 3 zeros. And then L is the number of U's. The U terms come from the denominator, which are colored in blue. So L is the number of blue lines. So L is 3. And N is just the total number of lines, right? So N will be here 5. So it's 3 blue lines and 2 red lines, right? So we can, this figure basically is going to be what we work with. It's a visual representation for each term in the product. And it, it's bijective with all of these stuff. So if you want to look at a particular coefficient, so look, if you look at the coefficient of v raised to k, u raised to l, z raised to n in this generating function, it will be partitions of k because the exponent of v is k. So it's partitions of k with L blue parts because the exponent of u is L and u's come from the denominator which are colored in blue, right? So it's partitions of k with L blue parts. And since z counts the total number of parts and z is the coefficient of z is n, sorry, the exponent of z is n, and there are L blue parts, that must mean there are n minus L red parts, right? Because the total number of parts is n, which is the exponent of z. So the coefficient of v raised to k, u raised to l, z raised to n is all partitions of k with L blue parts and n minus L red parts. And when we say parts, we include 0 as a part, right? So here, for example, number of parts is 5. We've included the 3 parts that are on 0. So is this way of representing these product terms clear?
No, we need time. We need maybe just one. Could you relate it to the partition function, meaning the generating function? Could you go back one slide, please? So all this exercise was to just prove this last statement that you have, right? You give us a couple of, or at least a minute to stare at it and see if we can understand the last. So that's the claim at the bottom, right?
Right, yeah. Right.
Yeah. Partitions of,
Maybe what is confusing is saying that this is a partition. I could say these are figures of weight k. So a figure is of the kind that we have just drawn, and then I can define the weight of a figure is just the sum.
n minus red parts.
Is the sum of the levels occupied by all of the pieces.
or perhaps it's two partitions, a blue partition and a red partition.
Yeah, that could also be. I could call it like
red
it's a,
partition has distinct parts and the blue partition can have repeated parts.
I could simply say the weight of a figure is just the weight of the levels that all of the pieces occupy. Sorry, is the sum of the levels that all of the pieces occupy. And so the coefficient of v raised to k, u raised to l, z raised to n is all figures of weight k with L blue parts and n minus L red parts.
See, I am thinking maybe you can, I mean, if it is only me, we can go on, but I suspect maybe
I
I'm
can
not
do,
around.
I can think of, I can mark the parts here. So this would be, for example, this is a u v0 z, and this is a u v0 z. This is a v0 z, v1 z, and a u v squared z. Right. So on this figure, and then I can define the weight of this figure to be just the sum of the levels that each of the pieces occupy. So this piece occupies 2. So it's 2 plus 1 plus 0 plus 0 plus 0. So it's 3. So the weight of this figure is 3. So then I can say the coefficient of v raised to k, u raised to l, z raised to n is all figures of weight k with L blue parts and n minus L red parts. Is that clear?
Yeah. Yeah, it helps. Can we go back to that slide, please? So in terms of, if I put u is equal to z equal to 1, the denominator is just the generating function for the partition.
Right.
And then what is the numerator is what? If I put z equal to 1,
Distinct
is
partition.
the distinct parts.
Right.
So in terms of that, is there an explanation to what you're doing? That's the way I'm thinking, but maybe.
If this partitions part, we can like I will bring this back later. But if we can understand this simply in terms of figures and their weights, then that's I think good enough to
Okay.
go on.
Okay. Sorry, I've interrupted you enough.
No, it's fine. I mean, this part has to be clear. But if we can understand this simply as so the coefficient of v raised to k, u raised to l, z raised to n is all figures of weight k with L blue parts and n minus L red parts, right? And just recall the weight of a figure. So for example, the weight of this figure will be all of the sum of the levels that the pieces occupy. So it'll be 2 plus 1 plus 1 plus 1 plus 0. So the weight of this figure will be 5, right? So the weight of the figure becomes the exponent on the v. The number of blue lines becomes the exponent on u, and the number of total lines becomes the exponent on z.
So it would help if you rewrite that v to the which is k, which is l, which is l, which is power.
Oh, right. I can write it in colors. So
Yeah.
v raised to k, u raised to l, and then z is raised to l plus n minus l. So the number of blue parts is l. Z is just the total number of parts. So it's the number of blue parts plus the number of red parts. And the weight of the figure is k.
Okay, I think I got it. Thank you.
Okay. So once we get comfortable with thinking of it in terms of these figures, we can describe the involution. The involution, there's a simple rule for the involution. We look at the largest piece. So
sorry to interrupt you again. So now what are we doing? Are you we are looking at this involution in order to prove something?
Right. So the idea
that we are proving. Just remind us.
Right. So the idea is that this signed moment is an alternating sum between moments of HKEL type term. And so what we want to do is we want to define an involution so that terms in adjacent, so that figures that are contribute to adjacent moments cancel out with each other. So basically we are defining a sign reversing involution. So each figure will cancel out with a figure either with the k value one higher and L value one lower, or it will cancel out with a figure which has k value one lower and L value one higher. So basically we're defining a sign reversing involution.
Okay, so just one more question. So we are taking this, okay, there are two things here. On top, you have these moments. You are claiming that the moment is given by the coefficient of something, right? That is one thing, right? Now, is that clear, or is that you're assuming that, or you proved it, or what is the status of that?
No, I'm just stating it here. It's proved in a paper, but I don't want to include it.
Okay, so these are, you are asking us to take it at face value, those statements.
Right,
Only that.
yeah.
Okay, and you are proving this the bottom half.
No, this is also to be taken at. I'm going to give an interpretation for these because this is now a virtual sum. It's an alternating sum.
Yeah.
So I'm going to express it as a purely positive sum by the end.
Okay, so you are just trying to compute this right hand side of this thing.
Right.
Is that okay? Got it. Okay, thank you. Oh, this the bottom half is just the earlier. Okay, it was just from, it follows from what you wrote earlier, right? So okay,
Right,
got
yeah.
it, got it, got it, got it. Thank you.
So okay, actually brings up an interesting point. If you look at adjacent terms in either of these summation, what you will notice is that the k term is one higher and the L is one lower. So for example, you can look at hk plus 1 EL minus hk plus 2 EL minus 1. So always if you look at adjacent terms, the k value will be one higher and the L value will be one lower to the right, right? So we'll always, whenever you increase the k by one, you decrease the L by one as well. So that's something to keep in mind as we describe the involution, because that's what the involution tries to do. So the rules of this involution are: you look at the largest piece. If the largest piece is blue, you push the piece up and change the color to red. And if the largest piece is a red, then you push the piece down and change the color to blue, right? So let's look at this example. The largest piece here lies on the third level, right? So there are three pieces that lie on the third level. One of them is red and the other two are blue. Now, if the largest piece is blue, even if there is a red, even if there's a red piece here, blue is given priority, right? We always try to push up first, and if we can't push up, then we push down, right? So in this case, we can push up because there's a blue piece. So we push it up to 4 and change its color to a red. So from here, we've pushed up a blue piece to the 4th level and changed its color to a red. Now, if we apply the involution to this thing, the middle one here, then the largest piece is now on level 4 and it is a red piece. So we try to push up, but there is no blue piece to push up. So we are forced to push down, right? So we push the red piece down and then change the color to a blue. So we push from 4 back to 3 and then change the color to a blue. And note the changes that occur in the K and L as we do this. We start with the K, which is the total weight. So it's 1 plus 3 plus 3 plus 3 plus 0, 0, 1, 3, 3, 3. So the value of K is 10 here. L is the number of blue pieces, which is 3. And N is just the total number of pieces. That's not going to change. It's 5. Yeah, that's 5. Right? So we go from here to, when we push the piece up, we are increasing the K by 1. So this is 3 plus 3 plus 4 plus 1, which is 11. And the number of blue pieces has decreased by 1. So L has decreased by 1. Right? So K has increased by 1 and L has decreased by 1. Right? So that's the idea. So it's going to map to something which has the opposite sign. Right? Again, when you do this, you get the original figure. So you're going from 11 and 2 to 10 and 3. So either K increases by 1 and L decreases by 1, or K decreases by 1 and L increases by 1. So that's the idea of this involution. Are there any doubts about this process? Just the involution itself.
If there is a tie, what do you do?
So like here, if there is a red and a blue piece, we prefer to push up. So we always push the blue piece first.
Okay, you always pick the blue and push it.
What if there is a if there is a okay, I think okay, got it.
And I guess
Thanks.
there will not be a red piece there because it is the largest. So we can stop.
They could, if there are both red and blue pieces, we always prefer to push up. So in the second involution, the things is reversed, but the common idea is that we try to push up, and if it's not possible to push up, we push down. And for this involution, those two steps are sufficient. So the blue piece we can push up, so we push up to a red, and a red piece, if we are forced to, we must push it down. So if this involutive process is clear and it's clear what's happening with the K and L values, then we can reimagine this virtual sum. So each of these moments for the HKEL, right? So each of the moments for the HKEL terms, they are the cardinality of some set of such figures, right? And based on the values of K and L, that determines the total weight of the figure, and it determines the total number of blue parts of the figure. So we can divide that set into figures that have a largest red top and figures that have a largest blue top, right? So for example, this would be a figure which has a largest blue top. Even though it has a red top, if it has a blue top, it goes to blue. This would be a figure, this would be blue top. This would be a red top, right? Because the top is red or the top is blue. So each set, you can divide it into figures where the largest piece is blue and figures where the largest piece is red. And the idea of the involution is that it takes a blue top figure to a red top figure in the next group, right? So it takes a blue top figure in HK plus 1 EL to a red top in HK plus 2 EL minus 1, right? And it takes that figure back to the original figure because it's an involution. So because of this involution,
No, except in the trivial case when there is nothing.
But there will be nothing, I guess, when E is 0. So in that case, it'll just be the sign and trivial in HK, which I think is already, we know that.
But there should be some cases where the involution doesn't apply, right? Which will be the what you're left with after applying the involution.
Right. So all of these intermediate terms get cut. And so what we are left with is just this red part here. This red part here cannot cut with anything. If this sequence extended to the left, it would get cut with something, but the sequence starts at HK plus 1 EL. So it doesn't cancel out with anything. But all of these intermediate terms where I've drawn these arrows, they all cancel out. So all of the intermediate terms cancel out. Blues with the red.
That's what I see. There is a nothing, right? There is a meaning for 0. That is no blue, no red. That's also somewhere.
No blue.
No, the sum of the H and K coefficients add up to some constant, right?
Oh, I see. So can we look at your sum again, please? Sorry.
Wait, this sum?
Oh, it is K plus 1 second.
K plus L plus 1.
Oh, 1 second. I see. Okay. Thank you. K plus L plus 1 is the
largest one. So the final term will be negative 1 raised to L, H of K plus L plus 1, E of 0.
Okay, thank you. In terms of exposition, Sridhar, see, it would help if you write this again in the thing that where you're explaining. So
okay.
I mean, just a suggestion.
Okay, I can do that now as well.
Yeah.
So what we have is SKL n equals -1 raised to j h k plus 1 plus j e l minus j, and j goes from 0 to l, right? So this first term will be h of k plus 1 el. This corresponds to when j is 0, and then the last term will be corresponding to when j is l. We'll have h of k plus l plus 1 e0, right? And all of these intermediate terms will get cut because of the involution. So I don't know if telescoping series, but anyway, what we will be left with is the parts that don't map to anything. So it'll be the blue part of this should ideally map to something on the right, but there is nothing on the right. And the red part here should map to something on the left, but there's nothing currently on the left. So what we are left over with is the red part from the first term, which is hk plus 1 el, this red part here, and the blue part from the second term, which is hk plus l plus 1 e0 of l. But this second term is empty, right? And it's empty because the subscript to the e counts the number of blue lines, right? So here, if L is a subscript to the E, that means there are L blue lines in every figure in this set. And here there will be L minus 1 blue lines in every figure in this set. And similarly, here there will be 0 blue lines in every figure in this set, right? But this subset of the set is all of the diagrams which have a blue top, but they can't have a blue top because they just don't have any blue lines, right? So there will be no blue tops in this final part, right? I'll just repeat it. The subscript to the E counts the number of blue lines, and this set is the number of blue top figures in the last box. But this would mean in this last box, there are no blue lines because the subscript to the E is 0. So if there are no blue lines, there can certainly not be a blue largest line, right? So the second set is empty. And what we are left over is just left over with is just this first set. So it's just hk plus 1 el and all figures here that have a red top, right? So now we will try to reinterpret this in the language of partition. So let's see how we do that. So look at this example here. We have a figure which has a 2 and a 1 and 0, 0, 0, right? So we can write this as a partition. We can write it as a partition 2 and then a 1. And for our purposes, we count the 0, 0 parts as well. Right? So there are 3 0 parts, 1 1 part, and 1 2 part. This is not all of the information that is in the figure. The figure also contains an additional piece of information, which is where the red lines occur. So one of the red lines occurs on 2, and the other red line occurs on 0. So all of these figures are a partition and a choice of certain distinct parts of this partition. Right? So the choice of certain distinct parts of the partition is where all the red lines occur. So what we are counting is all the figures in hk plus 1 en, where the largest part is red. So that would mean the total size of such a partition. So from this figure, you can get to a partition and a choice of something. So the total size of the partition would be k plus 1. And the largest part is a red line, is purely a red line. There cannot be any blues on there, right? So the largest part of the partition is distinct. So we're looking for all partitions of k plus 1, where the largest part is distinct because it has a red line on it, right? But this set is in bijection with partitions of k just by adding a box, right? So if you add a box in the first row to every partition of k, you will get a partition of k plus 1 where the largest part is distinct, right? So instead of considering all partitions of k plus 1, we can think of all partitions of k. That's where we have this. So we think of all partitions of k with, this term no longer has a unique largest part. All partitions of k with at most n parts, because each line is a part of the partition, right? In this interpretation, so each line is a part of the partition, and we have a total of n lines. So some of them could be 0. So the size of the partition is at most n. So we're looking at all partitions of K with less than or equal to n parts, and we must then choose where all of the red lines are, right? So uh, we must choose how many there are L. So we must choose L distinct parts of the partition, but there's a catch because the first row must always be chosen, right? So we must choose n minus L minus 1 because there are L blue parts, so there are n minus L red parts. So we have to decide this. So first we need to pick a partition of K. And then we must choose n minus L minus 1 distinct parts, and these correspond to the red lines, right? So they, yeah, so all of the red lines lie on different parts. So obviously each part in this figure, so each piece in this figure corresponds to a part of the partition obtained from this figure. So the total size of partition is going to be K, because, well, it is actually K plus 1, but we know that the first part is distinct. So instead of considering partitions of K plus 1 where the first part is distinct, we simply consider partitions of K because it's bijective. And then once we have a partition of K, we must pick n minus L total distinct parts, but we already know one of the distinct parts is the first one. So there are n minus L minus 1 remaining parts that we must pick, right? I don't know if this is clear. We are trying to reinterpret this set over here. So this set over here is all of the figures which have weight K plus 1, and there are L blue parts, and the top part is red, right? And we can think of a figure like this as a partition and a choice of certain distinct parts of that partition, right? So we're going to pick a partition of K, well, of K plus 1 technically, but the first part is going to be a distinct part, so it is unique. So the first part is unique. So we may as well pick a partition of K and just add a box to the first one. So once we've picked the partition, we must pick where the red lines lie. One of the red lines lies on the first part, which we know. So we must pick the remaining n minus L minus 1 red lines, right? So that's why we're picking n minus L minus 1 distinct parts. So the result of all of this is that the sign moment is this sum. It's a sum over all partitions of K. So the reason I've said uh, partition of K plus N is I've just added a virtual vertical strip here, because we've instead of considering these 0 rows, we can just add like a vertical strip of length n, and then all of the 0 rows become rows of length 1, and then we can just talk about removable cells without making making like a footnote like this, like include parts of length 0, etc. If I just wrote this in terms of lambda is a partition of K, I would have to make a condition based on whether or not the 0 parts exist, etc. So I'm just adding a vertical strip of length n to write this formula better, so to speak. Right, so we look at all partitions of length K, attach a vertical strip of length n to them. So now this is now a partition of length n, right? So L of lambda is n. So we're looking at all partitions of length n exactly, which are also partitions of K plus n. And we must make this choice. We must choose n minus L minus 1 of the removable cells, which do not include the first row. Why are we choosing removable cells? Because we want to choose distinct parts of the partition, and the number of distinct parts of the partition are equal to the number of removable cells of that partition. Right? Each block of parts of the same size contributes a single removable cell. So the number of removable cells of a partition just tell you how many distinct parts there are. And since we already know that one of the distinct parts is forced to be the first one, we don't include the first row in this count of removable cells, right? So we look at all removable cells that do not lie in the first row, and we choose n minus L minus 1 of them. And if you sum over this range, that is a combinatorial interpretation for the sign moment. And as a corollary of this, it's easy to see.
Have you, okay, you have written there. Can we, where is it written? Sridhar, can you just summarize that? You have already done it. I'm wondering if you have written it somewhere.
Which part?
So this, you said that the moment of the sign, or this is a trivial?
This is a sign.
This is a sign is equal to the number of partitions of what, k plus n, or what was that?
Yeah, it's a sum over all partitions of k plus n which have length exactly equal to n.
Okay, that's what you have written. Okay.
And it's a sum of this expression where rem of lambda is the number of removable cells of the partition lambda which do not lie in the first row.
And choose n minus 1. Okay, very good. Yes. Yes, I agree. Thank you.
Right. And then because of this is the easy consequence, see that S of KL, this sign moment is 0 if K is less than n minus L, choose 2. And this is because we have to remember that the total size of the partition is going to be K. Let's forget about the vertical strip, the n length vertical strip for now. So the size of the partition is going to be K. And we have to choose n minus L minus 1 distinct parts. So the smallest possible size of the partition is if these distinct parts are 0, 1, 2, 3, etc. up to n minus L minus 2, right? Because 0, you have to choose n minus L minus 1 of them. If you start at 0, then the largest one will be n minus L minus 2. But the removable cells do not include the one in the first row. So you will have the smallest size that a partition can be is it can be it can be 0, 1, 2. I mean, these are the parts of the partition. The partition can have parts 0, 1, 2, 3 up to n minus L minus 2. And then the first row must be n minus L minus 1, right? If you want the smallest possible partition. So let me recall what I'm saying. This term is choosing distinct parts of the partition. So what is the smallest size that a partition could be to still have n minus L minus 1 distinct parts and include a first row as well, right? Which is also distinct. So the partition could be 0, 1, 2, 3 up to n minus L minus 2. And then the smallest first row size would then be n minus L minus 1. So this would be a staircase shape. So it would be 0 and then 1 and then so on to this will be n minus L minus 2. So these would be the distinct parts that you pick. And then there would be the first row around this. So this is the first row. And the smallest size that the first row could be is just one more than the previous one. So it's n minus L minus, so it's just a staircase shape. So 0 up to n minus L minus 1, which if you add those up, it's n minus L choose 2, right? So I hope that this is clear. Okay. So the case for the trivial representation is very similar. The only difference between the generating functions for trivial and sign are that for the trivial, the u terms come from the numerator. So earlier, the blue lines denoted the number of the number of blue lines was L, but here the number of red lines is going to be equal to N. Okay. So the coefficient of v raised k, u raised to L, z raised to N is let's say instead of partitions of k, say figures of weight k, with L red parts because the coefficient or sorry, the exponent of u counts the number of red parts here, and n minus L blue parts. So the roles of red and blue are reversed when we consider the trivial representation. But the way we visualize them is still the same. And so I'm going to skip that part. And the involution is slightly, well, you need one more step too. So the involution for sign let me just recall for the involution for sign. It was if you have a blue largest part, then you push it up to a red. And if you have a red largest part, then you push it down to a blue. And here the roles are reversed. So now if you have a red largest part, then you push it up to a blue. And if you have a blue largest part, then you push it down to a red, right? So the roles are exactly reversed. And this also brings in an additional challenge, because if you push a blue down to a red, it might clash with an existing red one level lower, right? Because reds cannot occupy the same spot. So suppose you're trying to push down a blue piece, you may not be able to do it because there may be a red just under the blue piece already. So you could not push it down, because then it would make two red pieces, right? So that's an obstacle. But it turns out that if you encounter something like that, you can just ignore that piece and go to the next level, right? So if you're unable to do any action at a level, you just go to the next level.
Next means below or
Yeah, one below, because
one
we
below.
start at the top.
And what if you have red pieces all the way down?
If you go one level down, you will find a red piece which was obstructing the blue from going down. So when you find the red piece, you will push the red piece up to form a blue.
Oh, you don't push this down, but rather you look for the next piece to push.
Right. Yeah.
Okay.
So I'll do two examples. So in the first example, we don't we're not obstructed, and then the second example we'll consider an obstruction. So we can start here and fill in these values for k and l. So again, k is 2 plus 2 plus 1, so k is 5. L is now the number of red parts, not the number of blue parts. So L is 2, and then n is 3. So here what happens is we look at the largest piece, which is a red. It's also a blue, but we always try to push up first. And if we fail to push up, only then we try to push down. So we have this red piece here, and we push it up from the 2 and change the color to blue. So from the 2, we push it up to a blue. Now again, let's consider this thing. Its total weight is 3 plus 2 plus 1, which is 6. And L is now 1, because L is the number of red pieces, and N is again 3. We just put 3 here. Right. Now let's do the involution on this second diagram. The largest piece is a blue. We cannot push anything up because we can only push reds up. So we fail to push anything up, so we push something down. We try to push the blue down and change it to a red. It doesn't cause any conflicts, so we just get back our initial figure. So it's an involution on this, right? So what we've tried to do here is we've tried to push the blue down, and since there is no red at this level, there is no issue with pushing the blue down. So we just we get the blue line that already existed on 2 and the blue line that we push down from 3 onto 2 and change this color to a red, which is our initial figure. So that is clearly an involution, and then this is 2 plus 1 is 5. This is the same thing. So, right? L is the number of red pieces. Now let's look at a case where we are unable to push down a blue. Right? So look at this figure here. The largest piece is a blue, and according to our rules, if you find a blue largest piece and there is no other red piece that you can push up, you are forced to push it down. So you try to push the blue down and change it to a red, but it clashes with the red that already lies at this level, right? And so what you do is you just ignore this blue piece on top here, and then you go down to the next level. So at the next level, which is a 2, you find a red piece. If you find a red piece, you must push it up and change its color to a blue. So that's what we do. So we take this red piece here, push it up to a 3 and change its color to a blue, right? Now let's again do the involution on this middle diagram. There are two blue lines on there are two largest blue pieces, right? So the largest piece is blue. If the largest piece is blue, that means we cannot push anything up, so we must push something down. So we push down the blue, or we try to push down the blue to the second level and change its color to the red. When we push it down to when we push a blue piece down to 2 and change it to red, we see that it doesn't cause a conflict now, because this offending red piece here has already been pushed up. So now when we push the red piece back down over here, it doesn't cause a problem. So we can do this. We're free to push down the blue piece to the second level, which is what we do. And we get back our initial figure. So the thing to note is it's in the sine case, the move that we did, suppose we took a figure and then we made an involution on it, and when we applied an involution to it again, the first piece that we encountered was always the piece that we moved last. But here it may not be, right? Like the piece that we moved is not necessarily always in the highest position. Like here, there is an existing blue piece, but the piece that we moved here is to 2. So if I did it here, the latest piece to have moved is not the largest piece. It's actually one below the largest piece. So even though in the trivial case, the involution does not really track with what the largest piece is, it still works. Right? It still works because it always only considers the top 2 levels. We never have to go below the level and the level -1. Right? So just to recapitulate, if you have a red piece, you push it up. If you have a blue piece, you try to push it down. But if you cannot do so, then you ignore that level altogether. And we always prefer pushing up over pushing down. Okay. So in case of ties, always choose the one that pushes up. So that's the involution, and it works the same way as the last one. We have these, we divide, so each of these moments is a cardinality of a set, and then we divide those sets into subsets of 2 types. So here, the thing to note is, even though I've colored part of this as blue, I don't just mean the ones that have a blue top. I mean the ones that have a blue top and do not have a red piece just under the blue top. Right? Those are the only ones which go to the left. Right? For example, here you have a blue top here, and then if you carry out the involution here, the k value reduces. But here you have a blue top, but because you can't carry out the involution on the blue top, the k value in fact increases. Right? So the blue sets here, which match with a red set to its left, are not just the ones that have a blue top. They are the ones that have a blue top and do not have a red piece just under the blue top, right? But otherwise, the involution works the same. All of the intermediate pieces cancel out, and then we have only 2 parts. We have this this set from here, hk plus 1 en, which I've remarked is not all of the blue tops, and we have the red piece from here, hk plus l plus 1 e0. But again, the subscript of the E in this case counts the number of red lines. And here the subscript is 0, which means that there are no red lines in any of the figures in this set. Therefore, there obviously cannot be a red top, right? Because there are no red lines in general. So this second set is empty. So it's like, even though it's set 1 minus set 2, the second set is empty. So it's just a purely positive sum. And so we need to count all of the figures from this first set that contribute to it. I just quickly finish because I have to give the tablet over to my flatmate to take a class. So we need to count, and then I'll continue on the laptop after. So the leftover thing, we have to count these figures. We have to count figures which have a bunch of blue lines, but on the top, and they do not have a red line here. Right? Those are the blue top ones. We could either count this, or we could count this set, or we could do the involution on this set and count the set that occurs 1 to its left. Right? It's equivalent, even though this set here is kind of a phantom set. It doesn't occur in the actual summation. Instead of counting this thing, we could count its image under the involution file, right? Which is what it doesn't really matter, but this is what I count in the code. So what happens when you carry out the involution on this? You take a blue piece, you're forced to push it down. So there is at least one blue piece on the top, and there may be some blue pieces here, but not a red, right? So, and then when you push down a blue piece, you get a red piece over here. There could still be some blue pieces on top, and there could still be some blue pieces here. And the total size of this partition is K, and then the number of red pieces is L plus 1. Right? So we've gone from a partition of K plus 1 and L to one of K and L plus 1. And similarly, we interpret this again as a partition and a choice of distinct parts of the partition. Here, the choice of the removable cells or the distinct parts are subjected to a uh, more slightly more rules. So the rules depend on the size of the largest part and the size of the second largest part. If the size of the largest part is is more than 1 plus the size of the second largest part, then the first removable cell of the partition must be in S in general, right? So the first row will be in S. Basically, the first row will be red. If A is greater than B plus 1, then the first row will be red. If A is exactly equal to B plus 1, we can be we are in a situation like this where uh, either the first or the second removable cell is in S. So either this thing is red or the thing above it is red. Okay. This particular thing can only occur when A equals B plus 1. You cannot have, for example, you cannot have a blue line here and then somewhere here you have a red line. So this is not one of the figures that will occur. If you have a blue line and a red line just under it, it must be blue and then red one below it, exactly one below it. So that must mean that the largest part is equal to 1 plus the second largest part. The reason such a thing cannot exist is because if such a thing did exist, it would push down, right? It would push up. So note that we are actually counting like the phantom red part to this. We are actually counting this set, which doesn't actually exist in the sum, but its cardinality is equal to the blue set here. So you cannot have a blue line separated by more than one from a red line, because in that case, the blue line would push down and it would be part of the things that match to the left of this phantom sum. It wouldn't be things that match to the right. Okay. So you have these rules, and then to implement these rules, this is a summation. So you divide the set of partitions of k or k plus n. So the k plus n is just to write the sum slightly easier. It's actually partitions of k, and then I've added a vertical strip of length n. So all of these partitions are ones with length equal to n, length llama equal to n. Oh, I've written that. Sorry. Right. So you divide the set of partitions of k plus n whose length is exactly equal to n. You divide that into two sets. Either the first largest part is equal to 1 plus the second largest part, or it's not. If it is not, it has the same formula as the last time. It's just all of the removable cells, not including the first one. And then you have to choose L of them, right? But you have to choose L of them because here we're counting L plus 1 red parts, but we know that the first red part is the first one, right? So the first one is fixed, so there are L left. So we're choosing L out of all of the removable cells that are not in the first row. But if, I should probably say, yeah, if lambda is in D, there is one more possibility. So even the ones that are in D, they contribute to this first sum here. But the ones that are in D, there is another possibility. So that must be counted separately. Right? So for all of the partitions in D, it is possible that the top level is not, what was it? Blue. The top level is not red. It is possible that the top level is blue and then one below it, it's red. Okay. So if you're confused because here I'm talking about blue and then later on I'm talking about red, what I've done is instead of counting the blue set, I've actually done the involution on it and and pushed down the blue. So I've actually done the involution on it and pushed down the blue, and I'm counting its image under the involution, which is the thing to its left, right? So that's why I'm talking about red here and not blue. So if I did this involution on it, the blue would push down to a red. Either there would be exactly one blue line and it would push down to a red, or there would be greater than one blue lines, in which case there would still exist blue lines on the top, but just below it, it would be red. Okay, so those are the two cases. So yeah, you have to count these two sums where this rem2 is just all the removable cells, not including the first two, because in the second one, the red line is not on the first distinct part, first largest distinct part. It's on the second largest distinct part, right? And then you still have L left over to choose, which do not include the first two largest distinct parts, right? And similarly, you have this corollary that says that the moment is 0 if k is less than L plus 1 choose 2. And that just comes from just the same type of condition as last time. So are there any doubts about this?
I don't have a doubt, but I have a question. Hello?
Okay, yes.
Can you, so you have, so your right hand side, you're counting the number of partitions with some properties, right?
Right.
Now that obviously has some representation theoretic meaning.
Oh, okay.
In terms of SN representations. So I don't know what exactly it is, because these are the number of these are not partitions of the same number, but of partitions of different numbers, right? K plus.
No, they're all partitions of
K plus N.
Yeah.
They're all partitions of K plus N. Okay, K is fixed, N is also fixed.
Right.
Okay, so maybe it's tantalizing to think that maybe there is an interpretation in terms of representation theory.
Yeah, actually, that Amri was also saying the same thing. And if we can find that, then we can maybe try to generalize it for more than hooks.
For non-hooks. Yeah.
Right.
Seems like an obvious thought. Okay. Yeah. Okay.
Right. But so far we've not. I mean, we don't know what the interpretation is on that.
Just maybe you could try this for a small non-hook or something and see an example or something.
Yeah, we've actually we've tried to do this for 2-row shapes, but it doesn't work for 2-row shapes. You get like a partial cancellation, but you don't get a purely positive sum. So
no,
yeah.
I don't mean that. I mean, okay, you're thinking of the proof. Okay, but I was thinking more in terms of just run an example where you count how many there are in you compute the moment at n, and then so it is some number, and try to interpret that number as the number of partitions of K plus N, maybe, but with some property.
Okay, so you're saying for non-hook shapes or for double hooks or something like that?
Yeah, I don't know exactly what. It's very speculative, but yeah. Yeah, obviously you've been thinking along those lines. Okay, that was my question.
Thanks.
Yes, Sridhar, I have a comment. In the beginning of your talk, I don't think you meant to say that, but it seemed like you were saying that these results are in this preprint here, character polynomial in the restriction problem. However, only up to the formula for the trivial multiplicity of the trivial representation as a generating function is in that paper. None of the involutions and nothing about the sign representation is in that paper.
Right. I meant to say that these results specifically are in that paper, and also
not the sign representation.
Yeah, but there's also this corollary here is also in the paper, but it doesn't use this method.
So just wanted to clarify that, because people may look for these things in the paper and not find them.
Okay, so your new thing is the involution and the sign. Is that correct?
Yeah.
I think this positive result that giving the multiplicity as counting something is major. I mean, it goes much beyond what was done in that preprint. So,
it is very nice. I agree.
It's a positive result.
Yes. Yeah. I agree that it's very nice, and it opens up perhaps interpretations of other things.
Yeah, let's give other people a chance to ask questions. So.
I just need to give this tablet. So
Sure,
can
go
I,
ahead.
can you enable sharing screen on the laptop? Because I just
Yeah,
sign
sure.
off on the tablet.
It's enabled. Yeah.
Okay. Yeah. Any other question?
Okay, yeah, let me ask a question. So a lot of this comes from this formula for this S sub hook in terms of the alternating sum of H's and E's, right?
Right.
So is there some generalization of that formula to other partitions, or is that just a unique?
Well, you can express any. You have the Giambelli identity, so you can express anything as uh, the Schur function for any representation. You can express it in terms of a product of hook shapes and an alternating sum over those products, right? Because of the Giambelli's identity. And I think that each term, so basically what you will have is an alternating sum of the product of hook shapes. And so for each of the terms in that alternating sum, I believe that you can express that as a purely positive quantity, but I don't know how to get around the signs in the alternating sum themselves.
Okay. So what do you want to do next, or which direction? Because you could either look for partitions which are not hooks, or you could look for other besides the sign representation and the trivial representation, right?
Yeah. So as Raghavan was saying, one direction is to just consider more shapes. So we were trying for two-row shapes, but it doesn't quite work out. So double hooks or stuff like that. Double hooks would probably be the next one, or rectangular shapes, stuff like that. So we could probably broaden these results over some classes, but I don't know if these are generalizable to everything. I don't know if this method works because we can do it for other representations also, like instead of just a sign and trivial. We have the generating function to do it for any representation, but the interpretation of the generating functions is difficult. So I feel like we need one piece to help with it.
Okay.
So I think the difficulty with two-row shapes lies in the fact that it relates to a very old positivity problem, which is that if you take vector partitions of a vector k comma l, an integer vector, and you look at vector partitions, then we know that this pk comma l partitions of the vector k comma l is unimodal in the sense that if k is greater than or equal to n, then pk comma l is greater than or equal to pk plus 1 comma l minus 1. So you're kind of increasing the distance between k and l, given that k is already greater than or equal to l. And then, but this difference, so finding a positive formula for this multiplicity of trivial representation would be to find a positive formula for this difference. And we don't know of such a thing. So vector partitions of k comma l minus vector partitions of k plus 1 comma l minus 1. If you know combinatorial interpretation of this difference, that would solve the case for the trivial representation for two-row representations of GLN.
Oh, so let me ask a dumb question. So the classic partition function is increasing, right?
Yeah.
Okay, now is there a combinatorial interpretation of the difference at each step?
Yeah, that's in Andrew and Erickson's book.
Oh, there is one. Okay.
Yeah.
Okay. What is that?
I think just geez, what was some simple thing was there in Andrew's Erickson. So yeah, I mean, maybe you just look at partitions which have a last part 1 of k and of n, and then you remove that last part equal to 1 and you get a partition of n minus 1. Does that make sense? Something simple like that.
Yeah, that looks right.
Yeah.
But that wouldn't generalize to these other kinds of partitions.
Now you have two variables, k and l.
Okay.
And yeah, I don't know. I mean, maybe I'm missing something, but there was a paper, in fact, proving this unimodality result.
No, but Amri, I have a question. See, when you say two-row partitions, I mean, keeping with the, of course, sign is different, but keeping with the trivial, what you mean is you want to keep the second row length constant and keep increasing the first row level only, right?
No. When you apply the, now you will apply the Jacobi identity. So then you will get HK minus HK plus 1 HL minus 1. So we're not using, so we're using Jacobi's identity. So yeah, so you're increasing.
No. My question was different. Okay, my question was, see, so you're looking, so you had a formula for the trivial in of Sn in this hook, right?
Yeah.
So instead of the trivial, for example, what can we replace it with? So you can replace it with the standard, because the standard has the property that it is stable, if you know what I mean.
Its character polynomial is x1 minus 1.
So
we can definitely, do the character polynomial analysis.
So when you say 2 row, I would assume that you're fixing the length of the second row, and that is
no, I'm talking about 2 row
GL,
for the GL.
Okay, yeah. 2 row of the GL. Okay, I got it. 2 row of the GL, but still trying the trivial.
Yeah.
Okay, got it.
So yeah, are there any more questions?
So I was wondering.
Sorry. Go ahead, Aritra.
Okay, so I was wondering, have you thought about this, like SLAM? So you proved this SKL with trivial and also with sign of n is 0 for some n less than k choose 2 or something like that. Have you, is this general for like S lambda n is 0 for some condition?
For trivial or sign, and for trivial and sign, and then you're saying for general lambda.
Yeah.
GL.
So you no for yeah, I'm saying replace the KL partition by lambda. So
Okay.
S lambda of n, where meaning take the trivial or the sign, whichever. Do you know when they are 0?
No, we don't know. Even for 2 rows, we don't
Because for
have a
both
condition.
of them, you had this if and only if condition, like 0 if and only if.
Yeah. For 2 rows also, we don't have it. What I am trying to do is for 2 rows where the second row is either 2 or 3. I think some similar method works there. But if the second row is very small, so either if it's 2, it works for 2, and second row is 3, I think it works. So I'm just trying the same thing, but the same thing probably doesn't work in general.
Okay.
I think for 2 row partition we have some computational conjecture maybe that when the multiplicities are positive.
Yeah, I don't know if that's if and only if.
Yeah, we have. I think if you take the second part to be 2 length, 2 box, then the multiplicity is positive if and only if the first part greater equals to n minus 1 into n minus 4 by 2. It just means coming from the computations. But yeah, I don't remember that we have proved or not.
You're saying the second part is 2.
Yeah, you take the partition k comma 2. Just use
Okay.
the partition, 2 row partition k comma 2. Then the corresponding multiplicity of the sign is positive if and only if k exceed n minus 1 into n minus 4 by 2.
Okay.
It's, I'm just looking at the notes and just telling you. I don't know the.
I have one more question, ma'am.
Positive,
so is
like
there
for any
a,
lambda and mu?
Oh, sorry. Go ahead.
Sorry.
These restriction coefficients, these R, lambda, mu, are they expected to be positive? And as n goes to infinity?
Uh,
Or from your computational,
So
from
if
your
you fix,
computations?
if you
do
fix
you-
lambda,
Do you mean in general or for this, for hook shape?
Yeah, just generally, what do the computations suggest? Like
This
for,
lambda, I think this lambda stabilize at some place, right? When it is for a fix a lambda, then you increase the n. After some stage, the value is going to stabilize, right, Amri?
yeah, if you fix lambda, then only some finite set of mu's will occur in that. On,
oh, okay.
I mean mu's with padded with.
Yeah, yeah.
Yeah.
Yeah, the first row is.
Yeah, this is Monaghan's theorem, probably.
It's just stability. There's some
Stability, yeah.
Okay, so they're mostly zero. So all but finally many are zero
right,
for a fixed lambda.
right.
Okay.
I have, so is there a Rubinius reciprocity?
Yes. That's a different paper we have. There's an induction, there's a polynomial induction functor from Sn to GLN.
Aha, so maybe I've heard about it, but not understood it. So, so briefly, what is it? Can you say it in a single
So it's
sentence, or
a
would
sort
it?
of Mackey induction. You want to induce a representation from Sn to GLN, but you want the induced representation to be a polynomial representation of GLN.
Yes.
You look at polynomial functions from GLN to C, which transform under Sn, polynomial in the entries of the matrix.
Yeah,
Transform under Sn in a certain way.
Yeah.
That's it.
And then the same thing holds?
It
The
has
same
Rubinius reciprocity
in the usual sense holds.
in the usual sense.
So if you interpret it this way. Wow.
Yes.
Okay, that's nice. That's nice. And what if you do it rationally then? I mean,
Yeah, you could do it rationally. Yeah. Yeah.
Well, that opens up.
I haven't written that down, but there's no reason why.
Okay, thanks. Yeah, that's nice to know.
Okay, so any more questions? I guess we went.
By the way, this arc sign, what is the what's the duration you're envisaging?
Yeah, maybe it's unspecified, but maybe yeah, maybe I should make it 1.5 hours as a default. Yeah.
1.5 hours with questions.
Yeah, because I think it becomes difficult to ask enough questions and go in depth into it. Okay, so I'll just stop the recording for now. Thank you, Sridhar. Nice stuff.
Yeah, very nice talk.